recording.
Okay, so it's a pleasure to present Professor Carole Louis-Rose. She's an expert on partial differential equations and controllability. She works in France at the University of Antibes in Martinique, so it's in the American side of France, so close to Brazil and to Mexico and to this part of the world. So thank you very much for accepting to give a talk. Carole, you can start.
Thank you, Luz. So first of all, I want to thank all the organizers of the seminar, especially Juan Limaco and Luz de Teresa. Thank you all for attending my talk. So today I will talk to you about an approximate controllability problem of a non-local hyperbolic coupled system. During my presentation, I will follow this plan. First, in an introduction, I will present the system under consideration. Then, I will expose the objective of the work, and I will discuss the existing works in the literature. Some existence results about the main system and the dual one will be provided. And the main approximate controllability result is a consequence of a unique continuation principle that will also be given. At last, I will end with some of the main references. So we consider the system 1, which is a linear hyperbolic elliptic system, which acts on Q. Q here is equal to omega times 0 capital T, where capital T is a positive real number and omega is a bounded open set of Rn with a Lipschitz continuous boundary. So you can see that the single control G acts on the hyperbolic equation, and it is located on the hyperbolic equation, and it acts on the system through a non-empty open set O of omega. The solution of this equation is a couple YZ, which depend on space X and time T. And you can see that the system is submitted to an homogeneous exterior Dirichlet condition. So the main operator of the system is denoted by minor delta S. S here is an integer, is a real strictly between 0 and 1. And this operator is called the fractional Laplace operator or the fractional Laplacian. So now I will talk about this operator. So the fractional Laplacian is a non-local operator which can be defined for U in the Schwarz space S of rapidly decaying C-infinity function in Rn by the following singular integral that is to be understood in the principal value sense. The constants C and S, which is defined here, depend on the dimension n and on S. So we can say that the fractional Laplacian is used in the modelization of long interaction phenomena, whereas in the Brownian motion, you can use a Laplacian in order to model the short interaction between the particles. So we also define another operator that is denoted by minor delta SD. This operator is auto-adjoint and is given by its domain, which is a set of all function U in HS0 of omega bar, such that minor delta SU is in L2 of omega. And this space, HS0 of omega bar, denotes the set of all function u in Hs of Rn vanishing outside omega. Okay, so now here are a few elements about fractional order Sobolev spaces. So we let the real S be fixed between 0 and 1 strictly, and we let omega be open bounded set, an open set of Rn. So we denote by this quantity the so-called Gagliardo-Seminorm of a function u. And we let Hs of omega be the set of all function u in L2, such that this quantity is in L2 of omega times omega. With the natural norm, the norm L2 plus the Gagliardo seminorm of a function u, the Hs of omega is a Banach space. Moreover, it has been shown that this quantity defines an equivalent norm on the space Hs0 of omega bar, which dual will be denoted by H minus S of omega bar, and their duality pair with this notation. So you can find more information about these facts in the Hitchhiker guides of Dinesa and her collaborator in 2012. So our work consists in studying the approximate controllability of the hyperbolic elliptic system 1 by the internal control G. By this, we mean that the system 1, that for any state y1, y2, z1 in this space, and for any positive real number delta, you can find the control G in L2 of O times 0t, such that the corresponding solution yt of z satisfies the following identity. To prove our results, we will analyze the approximate controllability by a single control of another system, which is a system of hyperbolic coupled equation depending on a non-negative parameter and converging towards a parabolic elliptic coupled system. So some remarks have to be done. The first one is that by setting u at the integral from 0 to t of y, the first component of our solution, and v, the integral from 0 to t of z, the second component of the solution of the system 1, and using the following initial condition, that is that u in 0 and v in 0 are 0 in Rn, our main system can be converted into the following parabolic elliptic coupled system, in which you can find the following integral memory term. The second remark is that if our initial system 1 is approximately controllable in time, so that the system 4. Indeed, if the system 1 is approximately controllable in time, what does this mean? It means that there is, for any given state y1, y2, z1, this inequality holds, and in particular, you can deduce that the norm of yt in capital T minus y2 is smaller than delta, which is written here. But if you use the change of variables that u is equal to the integral from 0 to t of y, this inequality becomes the norm of u in capital T minus y2 is smaller than delta, and this inequality means exactly that the system 4 is approximately controllable. So now we are going to talk about a little bit of literature about approximate controllability problem. So in the internal case, the approximate controllability of the following it equation with memory integral term has been studied by Barbu and Iannelli in 2000. From their result, they also deduced the boundary approximate controllability result. Then we can cite the work of Tao and its collaborator in 2014, which analyzed the approximate controllability of the following it equation with memory using the semigroups theory. In particular, the result has been proved under the condition that the coefficient A here is strictly bigger than minus lambda 1 squared over 4, where lambda 1 is the first eigenvalues of the Laplacian. We can also mention Zhu and Gao, which showed in 2014 that the equation 5 cannot be null controllable at time capital T positive if the coefficient A is non-zero, but they also show the approximately controllability results if the coefficient A is strictly negative. In the exterior case, we can cite this work where the parabolic elliptic coupled system, which is here, has been studied. The author shows the approximate controllability results by the exterior control G, which is in the component U, or H in the component V, under the following condition on the coefficient of the system. Here, lambda 1 denotes the first eigenvalues of the fractional Laplacian. So, the first step of the proof of our results consists in converting our main system. So, the initial system, which is a hyperbolic elliptic coupled system, can be formally approximated by the following hyperbolic system, that is system 7, in which we add the red term depending on the non-negative parameter epsilon. So we can notice that a similar formal approximation has been used in the work. It was the approximation of a parabolic coupled system by a parabolic elliptic coupled system. And this has been used in the work of Fernandez-Cara and his collaborator in 2013, and the work of Lopez and his collaborator in 2000. We also had the work of, I think it's Puel too. So now, we are interested in the approximate controllability of the hyperbolic system 7. By this, we mean that for any given state y1, y2, z1, z2 in this space, for every positive real number delta, and for every positive parameter epsilon, we can find a control G in L2 of O times 0 capital T, such that the solution y, yt, z, zt of the system 7 satisfy the inequality 8. And here we have our parameter epsilon. Now I am going to give some properties about the spectrum of the main operator, and some notations that will be useful for our work. So we let lambda k be the sequence of eigenvalues of the operator minor delta SD. It is an increasing sequence of positive real number which goes to infinity as k goes to infinity. We also denote by psi k the orthonormal basis of eigenfunction of this operator associated with the eigenvalues lambda k. The family psi k is total in L2 of omega and satisfies the following spectral problem associated to the exterior homogeneous Dirichlet condition. So I refer you to the work of Serrade and Valdinocci in 2014 to have more information about these facts. Now, for every integer n and for every positive real number epsilon, we introduce the following notation. So delta n will be lambda n squared of plus 4a, the coefficient a. Rn plus minus will be minus lambda n plus minus square roots of delta n over 2 when it exists. And gamma n will be a roots of delta n with positive, imaginary, and real parts. Similarly, we will denote by delta n epsilon lambda n squared plus 4 epsilon d. Rn epsilon plus minus lambda n plus minus square roots of delta n epsilon over 2 epsilon. And we will denote by gamma n epsilon a square roots of delta n epsilon with positive, imaginary, and real parts. We can notice that if the coefficient a is bigger than minus lambda 1 squared over 4, so lambda 1 here is the first eigenvalues of the fractional Laplacian, we have that delta n is positive and that its square root gamma n is a positive real number. Otherwise, we can find an integer denoted by n0 such that for all integers smaller than n0, lambda n is less than 2 square roots of minus a. And we deduce from that that delta n is strictly negative and that its square roots is pure imaginary. Some similar results have been proved for the coefficient d when it is compared to minus lambda 1 squared over 4 epsilon. At last, we also prove some useful properties for the real rk minus, rk plus, rk epsilon minus, and rk epsilon plus, depending on the sign of the coefficient a and d. Especially, we are interested in the cases where a and d are positive real numbers. For example, if the coefficient a is positive, we have that for every integer k, rk minus is less than r1 minus, which is negative, and r1 plus is bigger than rk plus, which is positive. We also obtain this result for the multiplication of the real rk by lambda k. So now we are going to move to the second step of the proof of our main result, that is well-posedness results for the main system and for the dual system. First, we begin with the definition of the Weck solution of the hyperbolic coupled system. So if we let A, B, C, and D be real numbers, the control G in L2 of Q and the initial state in this space, a function y, yt, z, zt is said to be a Weck solution of the hyperbolic system 7 if y its second derivative with respect to time and z has these regularities. Then for every phi sigma in hs0 of omega bar and for almost every t between 0 capital T, both identities hold. And at last, the solution satisfies the homogeneous exterior Dirichlet condition and the initial state. Let us notice that if we denote by UV the solution of the system 7, if you look at the system 11, I'm sorry, it's the hyperbolic system with the control G, but with 0 initial condition. Moreover, if we denote by W psi the solution of the system 12, which is the hyperbolic system without control, but with the initial condition including U0 and V0, we can notice that the sum of UV plus and W psi is solution to our hyperbolic coupled system. So we will have to study the regularity, the existence and the uniqueness of both systems 11 and 12. Moreover, we prove that if the system 11 is approximately controllable, that is a system with the control but associated to 0 initial condition, so the system, the hyperbolic system will also be approximately controllable. Hence, we shall be concerned with the study of the approximate controllability of the system 11 instead of this one of the system 7. So let us begin with the system 12. The system 12 is the hyperbolic system without control, but with the initial condition, including U0 and V0. So first, we rewrite it as the Cauchy problem 13. And in 13, we can see the main operator denoted by A epsilon given by 14 and its domain. So we can ask now, we can wonder why do we introduce the parameter epsilon? We introduce it in order to show the main operator and to compute its eigenvalues, which are the real number Rk minus, Rk plus, Rk epsilon minus, and Rk epsilon plus, under the condition that the coefficient Bc is 0. Here you can find the characteristic polynomial. So our existence result for the Cauchy problem is the following one. We assume that for every positive real number epsilon, the coefficient A, B, C, and D satisfies the following condition. So A and D are positive, but less than the minimum between lambda 1 R1 plus and lambda 1 R1 epsilon plus. BC is equal to 0, and either B is non-zero or C is non-zero. So under these conditions, the operator matrix A epsilon generates on the space H times H, where H is equal to HL0 of omega bar times L2 of omega, a strongly continuous semigroup denoted by capital T of T, given by this formula for every function phi in H times H, where in this formula, capital EK is equal to EK times identity operator, and EK is a family of orthogonal projection in L2 of omega. Just to have an idea of the proof of this result, we used the following lemma on C0 semigroup, which has been proved by Leiva in 2003, and which is useful to prove the existence of, by using the semigroup theory, of some partial differential system. So the main step of our proof are given here. So we let phi be an element of H times H. First, we compute the operator A epsilon applied to phi, and we write it like this, where the matrices AK epsilon and AK are commutative. And the last step, which is the most difficult one, is to show that the norm of the exponential of AK epsilon A capital EKT applied to phi is bounded by a continuous real value function depending on t. And we obtain this one. So this theorem proves that for every initial state U0, V0 in L2 of omega, the Cauchy problem 13 has a unique strong solution, capital Y, with this regularity. And then we deduce that the system 12, which is the hyperbolic system without control, possesses a unique Weck solution, W, WT, psi, psi t, with this regularity. So now we move on the system 11, that is a system with the control, but with zero initial condition. First, we introduce the following intermediate elliptic problem 18, which solution is a couple alpha beta, and the function g is defining Q with real value. So we show the following results. That is a well-posedness result for the elliptic problem. So we let the function g in L2 of Q, and we prove that there is a unique Weck solution, which is a couple alpha beta with this regularity given by formulas 19 and 20 respectively. In 19 and 20, we denoted by beta n and alpha n the scalar product of alpha and beta with respect to the nth eigenfunction psi n of the fractional Laplacian in 2 of omega. Moreover, we prove the continuous dependence of the solution with respect to the data G. To prove this result, we mainly use the method of Galerkin approximation. So now for the system 11 with zero initial condition, we prove the following results. So under the condition that the coefficient satisfies the following condition: A and D are real positive number, and BC is 0, and either B or C is non-zero. For each control G in H2 of 0 capital T, L2 of omega, such that G in 0 is equal to 0 in omega, the system 11 has a unique solution, which is a couple UV with this regularity and given by formulas 22 and 23. So in 22 and 23, we have the function Cn, Dn, and their derivative. So Cn and Dn depends on T and are given here. We can also say that we have to prove the uniform convergence of the series 22 and 23 in T, but in this space, it has 0 of omega bar. And to prove it, we use the following estimation on the function Cn and Dn. Now we move on the dual system. So the dual system is the system 29, which solution is a couple PQ, and the final states is given in this space. We prove that under the following condition on the coefficient, which are the same for every term final state, there exists a unique couple PQ with this regularity and given by formula 30 and 31. So in these formulas, you can see the function C tilde 1n, C tilde 2n, E tilde n, and D tilde 1n, D tilde 2n, and F tilde n. So C tilde 1n is given here. It depends only on T. D tilde 1n is given here. C tilde 2n is equal to Cn. D tilde 2n is equal to Dn. And E tilde n of T is equal to Cn of minus T. And F tilde T of T is equal to Dn of minus T. And moreover, we also prove the following dependence, continuous dependence with respect to the data. So now we move to the first step of our proof of approximate controllability. So which consists in proving a unique continuation principle for the adjoint system. So for every positive real number epsilon, we assume that the coefficients of the system are such that, so A and D are positive real number, which is strictly less than the minimum of both quantities, okay? But now we assume that the coefficient B is 0 and the coefficient C is non-zero. If we let O be a non-empty open set of omega, and we call the solution of the adjoint system 34PQ, our unique continuation principle states as follows. If the first component P is 0 in O times 0 capital T, so all the solution PQ will be 0 in Q. And these results follow from a strong unique continuation principle, which has been proved by Ghosh, Salo, and Ullman in 2020. And this lemma states that if S is strictly between 0 and 1, U is a function in H minus R of Rn for some real R, and if both U and minus delta SU vanish in some open sets of Rn, then U is equal to 0. So our unique continuation principle is a direct consequence of this result. And now this is our main result, that is the approximate controllability of the hyperbolic equation depending on the non-negative parameter epsilon. So under the same condition on the coefficient A, B, C, and D of the system, we prove that the system 35 is approximately controllable for any capital T positive and any control G satisfying this condition. So just to have an idea of the proof, we denote by U, UT, V, VT the unique solution of the system 11, which is the hyperbolic system with the control and associated to 0 initial condition, and P, PT, Q, QT, the unique solution of the adjoint problem 29 with the final state in this space. We multiply the first equation of the adjoint problem by U, the second one by V. We integrate both identities over Q and we add them. We find the identity 36. Now, it's remains to prove a density result. We set for every positive real number epsilon, capital R epsilon of 0 capital T at the set of all function U, V, UT, VT, epsilon VT in capital T, solution of 11, associated to each control G satisfying this condition. And we have to prove that this set is dense in this one by using a consequence of Albanach theorem. So we fix an element in this space such that the following linear form is 0 for any control G satisfying this condition. Then we introduce by the notation tilde another element of this space satisfying 38, so we can consider the adjoint system 29 with this final data. By combining 36 and 37, we get that the integral in O times 0t of Pg is equal to 0 for every control G satisfying this condition, from which we deduce that the function P is 0 in O times 0 capital T. So now it remains to use our unique continuation principle to prove that all the solution PQ is 0 in Q, and from the uniqueness of the solution of the adjoint problem, we deduce that the state phi t, sigma t, rho t, mu t is 0 in omega 4, from which we got our density results. So now I will give some of the main references that we use for this work. So here is the work of Barbu and Yaneli, where you can find the approximate controllability result associated to the heat equation with memory. Here you can find the Hitchhiker guides, where you can have more information about fractional order Froebel space. And in this work, you can find a similar formal approximation that we used in our work. The work of Ghosh, Salo, and Newman, where you can find the unique continuation property for the fractional Laplacian. And here the article of Leiva, where you can find the Lemma C0 semigroup. Now, all these results that I presented to you will be published in this article in 2025. There you can find the properties of the spectrum of the fractional Laplacian. And here you can find the article. We use some similar methods than has been used in the article. So I finish here, and I thank you everybody for their attention. Thank you.
Thank you, Carole.
You're welcome.
We now open the microphone for Professor Dimacon. If somebody has any question, comment, you can open your microphone and ask, or you can write a question in the chat. I have some questions waiting for other people. So you mentioned that there is a result by Stu and Gao of equation with memory, saying that the system is not non-controllable.
Yes.
The same thing happens for your system?
Yeah, I don't have the null controllability result.
Not a positive nor negative, nothing. You don't have a...
For the moment, nothing.
Okay.
Yes. That is a very difficult question. You can find in the literature that a lot of work about the null controllability of one-dimensional fractional equation has been proved. But even here, in one dimension, it is not obvious. Yeah.
Okay. I'm not used to this kind of questions. So I don't know really how. I don't know if somebody has another question. Somebody has a question or comment? I don't see.
I'd just like to thank Professor Carole for the nice talk.
Thank
you
you
very much for being here with us.
Thank you. Thank you, Marcia.